Alright, so if you're just coming in, alright, those of you who are just coming in now, hold off. Alright, you should have been handed it ready. I don't want to interrupt my lecture, because especially we're recording today. Alright? So just enough with the homework. We're going to record the lecture today. This is part of my deal, right? To help myself improve lectures and improve, therefore, your grades. Maybe I can improve my lecture style. This is going to be part of the whole grade stimulus package that I'm proposing. Alright, we'll talk about that in just a bit. So again, if you're just coming in now, hold off with the homework, okay? So also part of this grade stimulus package, I'm going to extend my office hours on Tuesdays and Fridays. Alright, so now periods 5 and 6 on Tuesdays and Fridays, same office, 2 a week. Sort of accommodate the influx of people that are coming to the office now because of homework. If you're going to come in late, just hold off on homework, right? To accommodate the influx of students that are going to come in the office to talk about their grades, their progress, and to have some extra help with the homework assignments. So again, Tuesdays and Thursdays will be extended. Do not hand your homework down if you're coming in late, okay? Just hold off a bit. Alright, is that clear? Alright, so this is sort of my gesture to all of you to help improve the course. One other thing that I'm going to do, alright, is sort of a score refund, if you will. Alright? This is what I call a score enhancement. Again, part of the overall package of my grade stimulus package. I'm taking this cue from my favorite pseudo-chemist, George Bush, over here visiting a chemical facility a couple of years back. Alright, I think the lad actually exploded a couple of seconds later. And so what I'm going to do here, alright, is right now talk about exam 1. The results from this first exam, which were kind of low. Now this is the grade distribution as it stands right now. These are not the raw scores. Remember, I added 8.33 points to everybody's raw score, so we're normalized to this top student over here. Well, what I did was, over spring break, is I reevaluated this normalization. And I am going to boost up grades. Again, if you're coming in late, just hold off on the homework, all right? I'm going to boost up grades just a little bit. This is part of my overall package here. So, what am I talking about? Let's assume that this one person here is sort of like, an outlier. Right? When you often work with statistics, you often negate the highest and maybe even the lowest scores. And so that's what we're going to do over here. We're going to cut off this one person. Okay, so they're obviously going to get over 100%. And we're now going to make this line over here, okay, which with this curve, at 234 being the max, this will now be the maximum. Alright, so we'll just translate that to this score over here into 250. So everybody, in a sense, is getting an additional 16 or 17 point boost. Alright, and that's because of the way, truncation works. So overall, when you think about it, alright, when you think about this, the raw score, the actual number you got correct times 8.33 points, has been increased now by what? Right, 3 questions. So that's 24.99 points. So this is going to really boost up a lot of the people, especially on the lower end, that are teetering on failing, for instance. Now obviously those people that have A's, or just have even stronger A's. And I really think this is going to provide a necessary boost to the course. I really do. Alright? So how does everybody feel about that? Is that okay? Okay. You're welcome. Now I'm going to keep this as it is on the weekend, because I'm actually going to go and upload the grades to EL, so they're not on there right now. Alright, so maybe about Saturday or Sunday when I get around to it, alright, there'll be the increase observable, and I'll leave any sort of grade enhancement or score enhancement to any later date, okay? So I'm just going to leave it at this for now. I'm not going to touch any of the grades until I see the results from exam number 3, which will be, what, 2 weeks or so? 2-3 weeks? Okay? Yes? I just said no. This is just exam 1. I'm going to hold off on any sort of other grade enhancement until I see the results back from exam 3. All right? So I'm not going to touch exam 2 at this point. When we look at first of all, the second reaction papers, grades were far better than the first one. So grades have been improving. I noticed this with the pop quizzes, the extra credit pop quizzes. I noticed this with the homeworks. So I do see some effort on your part, and that's one of the reasons why I'm giving out this score enhancement. Okay? So, that's that. Talk about any more on a later date, if any. I mean, I may not give out more points. Don't, rely or don't expect me to do so. All right. So that's that. Let's move on now to Chapter 7. All right, we're moving on to a new chapter. If you're coming in late, you're not handing the homework. All right, just fall off till the end of the lecture. New chapter, Chapter 7, the fires of nuclear energy. This is a very interesting topic over here. We're actually going to border on, let's say, some physics, for instance. I mean, there's a very fine line between nuclear chemistry and nuclear physics. And of course, we're going to bring this into the greater perspective of how all this applies to society. We talk about nuclear power plants and its relation to nuclear energy and how it relates to other forms of energy as given on the table, which we'll talk about in just a bit. So remember, if you will, that we said fossil fuels are certainly limited. These are limited resources, and our petroleum or crude oil reserves will run out based on the current trend. Now, of course, conservation may halt that process, but on the current trend, crude oil will run out in our lifetimes. This is going to be a truly global catastrophe. So we need alternative fuels to sort of boost up and accommodate for this lack of supply, even though we have ever-increasing demand. We talked about alternative fuels when we finished up with Chapter 4, and now nuclear energy, which really had quite a big boost in the 50s and 60s, and unfortunately went down a little bit, as you see in just a couple of slides after one of the nuclear accidents. All right. So unlike fossil fuels, nuclear energy is potentially unlimited. I mean, you get an incredible amount of energy from a very, very small mass of radioactive material. All right? And it's very, very clean. Of course, there's no atmospheric pollutants, carbon dioxide, carbon monoxide, oxides of nitrogen and sulfur. This is not present in nuclear energy as it is in the combustion of fossil fuels because, right there in itself, there's no combustion going on. All right? So very, very clean. Of course, right, we have to deal with such problems as nuclear waste. That is by far the biggest problem to date when it comes to employing nuclear energy on a large scale. You have all these spent fuel pellets. What do you do with them? They have to be buried somewhere for many thousands of years until they actually become calm enough to handle again. Another problem is, of course, radiation leakage. So a lot of people are concerned about some sort of explosion, as we saw in Chernobyl, and as we'll see today, or some mild radiation leakage as in 3 Mile Island, which happened in the late 70s. And I would say that that's really an overstated fear. The nuclear energy is very, very safe, but of course there is a small potential for just total global disaster. Leave that off to the side until a later time. But of course, what do we have over here? Nuclear energy is very, very efficient. An incredibly small amount, that is the mass needed to produce an incredibly large amount of energy. So what I have over here in this given table is comparing some of the main forms of energy. So uranium, which is the main fuel for nuclear power plants, in the form of uranium oxide, okay, used as uranium, and it's an oxide under our nomenclature rules from Chapter 1. So just with a little bit of 4 grams of uranium oxide, we can produce the same amount of energy as, what is this, 0.6 megagram of gasoline, all right, or 1 megagram of coal, or 3 megagrams of wood. So incredibly, incredibly small amount. In fact, this over here, this relative size picture, where we show this uranium oxide fuel pellet is smaller than a dime. It's only about 4 grams or so. So it's really an incredible, tremendous amount of energy that's been produced in just a small amount. And of course, very, very cheap. Very, very cheap for the fuel source itself. Now these prices, especially with the nuclear fuel, doesn't include the vast amount of cost that goes into the disposal, which when we get to the end of the chapter, we'll see it is an immense problem to deal with. So again, very, very small, a lot of energy being released. We'll talk about how it's arranged in a real nuclear power plant in just a bit. Okay? So now let's consider the power production in our country. And don't get this confused in the beginning of chapter 4 when we show power consumption. This chart over here is electricity or energy production. And we have, of course, the vast amount in this country produced by coal, over 51%. And about 20% is nuclear energy. All right? This very clean, renewable fuel source. And you may think, that it's sort of a godsend, incredibly cheap, no pollutants. And for a long time it was, especially after World War II. Unfortunately, though, in the country, outside of Harrisburg, Pennsylvania, which is in the southeast of the state, in 1979, there was a little partial meltdown at the 3 Mile Island nuclear facility. And what happened was that people got really, really scared. And I would say for good reason. Unfortunately, that fear hasn't really lightened up. So since 1979, there's been a government-mandated moratorium or halt on any new production of nuclear power plants. All right? And in fact, over the years, there's been about 9 closings. Now they close on a natural basis because fuel cells run out, technology is outdated, and the government doesn't reissue the contracts for any sort of private or public company to produce the fuel and use the energy. Now again, even though we have this decrease in nuclear energy, there's still this ever-increasing demand for energy consumption in the United States, right? In fact, the world. So why are these things, nuclear energy decreasing? Well, because, there's quite a bit of fear, as we just said. All right? And I would think that it's really quite a conflict when we consider that nuclear energy is pollution-free. And I really think that, as time goes on, people are becoming more and more eco-friendly. They're more cognizant of the dangers of overpolluting our atmosphere. And so even though nuclear energy provides a solution, it really hasn't taken off as the degree that we would expect. So, that's something we have to consider as a society. All right. So where did all this start? How was this first realized? Well, like most modern-day physics, it started with Albert Einstein. All right? And his very famous equation, E equals mc squared, which we'll do a little bit of math on, which I think may be the last math equation we're going to work with for the course. Okay, I think so. The chapters towards the end are more qualitative and concept-based, and I really don't think there's any more math past this. Okay, so what we have over here is this proportionality between energy that is able to be released from a certain change in mass. All right? This mass, however, you got to note when we do the calculations, is not in grams, it's not in base units, it's actually in kilograms. All right, we'll see this in just a bit. And c, of course, the speed of light. We saw this before. You will be given this again on our third exam. All right, it's a very, very large number. And here now we're actually going to square that large number to get an incredibly huge number. All right, that's going to translate into an incredibly massive amount of energy that can be released from a very, very small mass. This is a very powerful equation. It really blew open the doors, so to speak, to the atomic bomb and to nuclear energy technologies. And we see this now in retrospect as really a revolutionary equation. Very elegant. We often say an elegant equation when it's very simplified, a few amount of terms over there and very, very powerful in its impact. And this is certainly one of the most well-known and elegant equations of all of science. Right? Unfortunately, though, Einstein's contemporaries really didn't understand it, or at least, I should say, didn't really grasp its applicability on Earth. I mean, what we saw here was the application of E equals mc squared to the sun. The sun is essentially a large fission process where you have hydrogen gas being converted directly into energy. All right? So this calculation was able to model the energy released from the sun, but it wasn't really observed on Earth until about, I think, 1939, 1938, okay? When the fission process was actually experimentally observed with the fissioning of uranium atoms. All right? So again, this really blew open the doors to everything that we know about nuclear technology, bombs and power plants, for instance. All right? And what we can see over here, this little graphic is, we have a uranium nucleus. We're not being concerned about the electrons at this point. Just the nucleus alone, when that's bombarded with a neutron, remember this is a particle with virtually one mass, a mass of one and a charge of one, all right, when this is bombarded onto the nucleus, you have now this fissioning process, where you have now the splitting of a larger nucleus into smaller nuclei, and also the subsequent release of further neutrons. All right, we'll see how this translates into a chain reaction event. Okay, and we'll see this a little more in depth when we talk about now uranium in particular, but this is going to be our main fuel source for nuclear power plants. All right, let's realize a couple of trends and facts that we know of. For instance, only a certain amount of elements are able to go under the fission process. And typically these are the heavier elements because they just become more and more unstable as the mass increases, as the number of protons and neutrons increases. We'll see this in just a bit. All right, so we look at the periodic table, all right, you look at the heavier elements. Well, it turns out that most of these, okay, we're talking like 90, 103, these elements down over here, those are pretty much all radioactive, very, very heavy. As you get more heavy, more massive, larger, okay, the nuclei becomes a little more unstable. And in particular, it's only certain isotopes of these elements that are unstable. Hence, we have now, for instance, two different isotopes of uranium. One which will be used as a fuel and one that will not be. So let's consider again uranium, okay? We could express it as a subscript over here, 92. That represents the number of protons. Recall that that subscript indicates its atomic number of protons. So you look at the periodic table over here, U is for uranium, 92. All right? So we just write this as a subscript. We can write the superscript over here as the sum of the protons and neutrons. Remember, this should just really be reviewed from chapter 2. All right? So, for instance, one particular isotope of uranium, of which there are at least two, is uranium-238. All right? Because there are 146 neutrons. 146 plus 92 equals 238. And again, you can write that atomic number, the mass of protons and neutrons, at the superscript over there. Again, this should be reviewed. And we can express this in words over here, uranium-238, U-238, or what the process I'm going to use over here is, or the technique that I'm going to use is a superscript 238U. Okay? So, like we said, there are isotopes, and only certain isotopes for some elements are able to go under the fissioning process. So, for instance, all right, we have a very small percentage of uranium-235, 0.7%. And this is actually what goes in the fissioning process for, let's say, bombs in particular nuclear power plants. So 92 plus 143 neutrons equals 235. All right, again, that same math that we just saw a couple of seconds ago. All right, so we're really just seeing the difference now of 3 neutrons. Just the difference of 3 neutrons between these two isotopes, begin to see a dramatic difference in the physical and chemical processes between these two. All right, so for instance, like I said, uranium-238 does not undergo fission, and 235 does. So we can now see this plot, or we can have this as a plot to sort of visualize this trend. Now let's realize first of all the periodic table. We often see the periodic table with these elements over here cut off and given on the bottom. We do that for the very, very simple fact just to make the periodic table a little more condensed. I mean, it fits nicely on a board this way, which is almost a square, than if we were to have a very, very long rectangle. But really, okay, really the periodic table is very, very long, and these groups of elements over here, which are called post-lanthanide and post-actinide elements, because they come after lanthanide and after actinide. All right, they fit it over here. So again, very heavy elements. All right, will be on this bottom row. Let's not get confused with the color coding. This is just from the figure that I was able to scan in the transparency from an earlier lecture. All right, by far, the heavier the element you go, the more unstable the element becomes, and the more readily it undergoes the fissioning process. So there are a couple of rules of thumb that we're going to acknowledge. What did I just say? Okay? Heavier elements are less stable than lighter ones. Okay? Only certain isotopes are unstable, and therefore only certain isotopes, like we saw with 235 versus uranium-238, can undergo this fissioning process. Now, there's another rule of thumb that we don't really have to know explicitly. This is something that I picked up from my chemistry class when I was an undergraduate. I think it's really cool. That turns out that when the sum, okay, I'm sorry, the count of both the neutrons and protons are even, they are a little more stable than when the numbers for the protons and neutrons are odd. So this is what we call the odd-even rule. All right? And if we plot this now in this chart over here, we can see a certain band of stability. All right? So we have over here, I know this is a very poor figure, and I'm pretty sure it didn't print that well on your slides. And I apologize for that, so this is not going to be the exam. But I do want to throw it in here because I think it's really cool to see the strength. As we increase the number of protons, so for instance from 1, this chart only stops off at 85, so we're actually not going to include radium here. We have the number of protons, or the atomic number on the x-axis. As we go up, it's a number of neutrons. Okay? And we would expect that most elements are about 1 to 1. You usually have roughly the same amount of neutrons as protons. But we know because of isotopes, that's not the case. So roughly this line is a 1 to 1 ratio. But yeah, we see some there. How do we say this over here? Some aberrations, I guess we call it, from the center line. All right? And we see over here in black are these naturally occurring, all right, isotopes, which are stable. What we see over here in the orange are isotopes that are naturally occurring, all right, and unstable. And in the white over here are going to be synthetic elements. We can actually produce elements by certain fusion processes, by linear accelerators. We're not going to go too much into that. All right? But I think it's really cool how we see this trend. And it sort of verifies what we talked about, where we need a certain number of protons and neutrons. This is just a naturally occurring phenomenon. That's it. People get this from observation, and we do a little bit of prediction when we graph this on a chart. That's all we really have to take home from that. All right. So, we're going to now be introduced to a new type of equation. We saw certainly chemical equations, all right, where we had products, reactants forming to products. We saw different molecules forming. Well, in a very similar fashion, we can have a nuclear reaction, all right, where now, instead of forming different molecules, we're going to form different atoms of different elements based on this fissioning process. Because essentially, we're going to split up an atom, all right? What's going to happen to the parts? They're going to form smaller atoms. And so we see over here this nuclear reaction, okay, with first uranium-235. Remember, this is the fissionable isotope. We're going to impart on it, through a bombardment process, 1 neutron. And that's going to yield, in a very temporary and a fleeting manner, this uranium-236. Right? We put this in brackets because it's just temporary. It's almost instantaneous. It never really happens in a real observable sense, except in a specialized laboratory. And that's going to immediately split up because this is going to be unstable, very, very unstable, immediately split up into 2 different elements. So we can actually produce elements from larger ones. So let's not get this confused. This is not any sort of transmutation as an alchemist would do 300-400 years ago. This is a real process, all right? And unfortunately, some of these products are actually going to be radioactive in themselves. So that causes a problem. I'll just leave it at that. But let's consider now the equation. How do we read this? All right? 2 things now. Much like we saw for the law of conservation of mass and energy with the chemical equation, for this nuclear reaction, we have to observe a sort of conservation with the subscripts and superscripts. Okay? So we see over here, uranium, 92 protons. The subscript is 92. Well, over here in this temporary element, okay, 92 also. And 56 and 36, well, that is also 92. So we have to have this sort of balancing, all right, like we saw in chemical equations with these nuclear reactions. That has to be observed, all right? And in fact, you can also use a sort of coefficient, as we saw before, to help with that balancing process. Let's look at the superscripts, where this would be concerned about the number of neutrons and protons. So we're imparting a neutron, so we have 1, okay? All right, that's the number we assign to that neutron. Imparting that or bombarding it with a uranium-235. All right, so 235 plus 1 equals 236. That's exactly what we see over here. When this undergoes the fissioning process, it splits up into 2 elements. We can actually form barium and krypton from uranium. All right. Again, these superscripts have to be conserved. So 141 plus 192. Okay, well that yet doesn't add up to 236. But remember we have neutrons over here. All right? And now we're actually going to have 3 neutrons because we have this equation balanced. And this, of course, will add up to 236. So we have to obey this certain conservation as we saw with chemical equation. All right? This is crucial. All right. So this is what I just said. All right? Now recall that there are isotopes. Recall that we give, let's say, atomic masses and these different numbers as nominal values. These are rounded values based on a certain atomic mass unit, AMU. Remember, we define this atomic mass unit within a certain exact mass. All right? So if we add up all the exact masses for both the left and right side of the yin symbol, we see that it's not equal. All right? Because, for instance, let's take one example of uranium-238. Even though we say it has a nominal mass of 238, that's not exactly true because we have to count in the actual masses of the subatomic particles. And so the actual mass would be 238.0507847 grams per mole. Quite a large number of significant figures. We can actually measure out to that degree with some very specialized instruments. So keep it in mind, of course, there are isotopes with, all right, exact masses. So what happens then after a nuclear reaction, right, is we have a certain loss of mass. So for instance, when we fission uranium-235, it turns out that 0.1%, right, remember we translate that into 1,000th, or 1,000th of the original mass is lost. So for instance, we have exactly 235 grams, okay, nominal mass of uranium-235, well, that's going to translate into 0.2 grams, which are lost. And in fact, this mass is lost as pure energy. Again, given by the Einstein equation. Okay? Does this make sense? All right? We're sort of oversimplifying things over here because we're using nominal masses, but the exact masses, when we do the math, there's a discrepancy. That discrepancy is because mass is converted to energy in this fissioning process. That's it. This is a naturally occurring phenomenon. Scientists observed this with experimentation. Einstein predicted this even before any experiments. That's why he's such an incredible genius. Right? He was able to predict it with this equation, and this equation very accurately models, again, this naturally occurring phenomenon. That's it. That's just the way life works. This is why I like science so much, because this is the way it is. I mean, there's no debate. All right? This is the way it happens. We just got to accept it. Okay, so let's do some math. Let's try to work with this mathematical equation. Now let's now assume we have about 1 kilogram, 1.0 kilogram of uranium-235. This is the fissionable isotope. Okay? 1 kilogram is about, 2 pounds, a little over. And when this goes on the fissioning process, we're going to lose, what did we just say, 1,000 of that original amount. Okay? So 1,000 of 1 kilogram, right, is 1 gram. I mean, kilo was 1,000. 1,000 of 1,000 is 1. Does that make sense? Okay? I think we should all be familiar with that in this point right now in the term. Okay? So we have 1 gram that's going to be lost in this particular equation, sample equation. So, how do we find out the amount of energy? E equals mc squared. You have to know this equation from the exam. I will provide you with C as I did before. Okay? This is a very simple equation, just plug and shove. Okay? Put in the value. Keep in mind, though, one very, very crucial thing. Mass now is not the base unit gram. Mass is going to be in kilograms. Alright? Don't get that confused. I'm not going to provide any hints on the exam for you. So, let's just plug it in. Okay? 1 gram, the same thing as saying 10 to the negative third kilogram. Alright? C, 3.0 times 10 to the 8 meters per second. It's a speed, it's a velocity. Again, we're going to be squaring that number, that very large number, squaring it to have an even larger number. This is why this equation is so powerful. We have such an incredibly large amount of energy to use. Now keep in mind, though, that when we square something, we not only square the values, okay? We not only square the values, but we square the units. So we get meters squared over seconds squared. Keep that in mind. All right, so when we do arithmetic over here, just multiply it out, okay? The value will be 9.0 times 10 to the 13. That's the value. All right, you do it in your head, you do it in your calculator, that's what you get. Okay? Remember now, we account for the units, so we're just going to multiply this across kilograms, meters squared per second squared. Now obviously, this is a little bit of a weird, complex unit. All right, we just got to know that this is defined as a joule. The international authorities that determine units in the metric system, they define a joule as kilogram meters squared per second squared. Again, we actually saw this at the beginning of chapter 4. We talked about this briefly. Now we have to know this and know this again. So the value is still the same. It's a one-to-one conversion. So you essentially, when you do your calculations on the homework and on the exam, just substitute J, joules, for these complex units over here. So from a very, very small amount, 1 gram, we get an incredibly large amount of energy. And in fact, this amount of energy is proportional to about 3,300 tons of coal. All right? Or 33,000 tons, 33 kilotons of TNT. Now, you often hear about kilotons when we talk about nominal yields for nuclear bombs, and it turns out that 33 kilotons is essentially, of course, the energy that was released from both Hiroshima and Nagasaki atomic bombs. Really quite incredible, from 1 gram. Now, of course, they use a lot more than 1 gram for the atomic bombs because as the bombs explode, the masses of the fuel, if you will, the center core is exploded. They don't really have the efficient fissioning process. All right. So we're assuming here in this calculation that every single bit, every last atom goes under the fissioning process. When in real life, for instance, a nuclear bomb, that doesn't really happen. All right. A very small percentage really explodes. Okay. Is that okay though? The calculation? I think it's pretty straightforward. I think it's fairly simple, so I don't really think there should be too much difficult with that. Okay. Let's now talk about a little more in depth about the fissioning process. Recall, if you will, that nuclear reaction, we had from the bombardment of 1 neutron, at the end, 3 neutrons being produced. So as you see over here in this graphic, okay, this is what we just showed, right, with the nuclear reaction. Schematically now, we show that 1 neutron being bombarded into an atom of uranium-235. What would produce is barium and krypton, like we showed before. And also 3 neutrons being produced. Well, what happens with the neutrons, okay? They're still going to be reactive, they're still going to now progress and sort of repeat this same process. This is essentially what the chain reaction is. So these neutrons now are going to undergo another reaction. They're going to now produce another fissioning process and impart on another uranium atom. I mean, there isn't just 1 uranium atom going on over here, okay? There's going to be a whole bunch. Okay? A very, very large amount. So this neutron can now be bombarded on another uranium atom. And this now will split into smaller atoms and release its own neutrons. Now, certainly there's more products than just krypton and barium, so we have over here cesium and rubidium. Likewise over here, with this 1 neutron that went that way, for instance, we have strontium and xenon. Okay, but we have more neutrons that have to be accounted for. Again, this chain reaction process. These neutrons are now going to impart or being bombarded on other neutrons, other atoms of uranium. So, what do we have over here? iodine, okay, and this actually is radioactive iodine. This is that really occurs in a nuclear bomb. All right. We have zirconium, barium, krypton, and so again, what is that? Ce. Okay, selenium, xenon, all this stuff. It's a chain reaction. All right, very, very rapid process. All right. However, this doesn't really happen to, let's say, a disastrous effect. All right, in nuclear bombs, I should say nuclear power plants. Remember, because in equals mc squared, we're assuming that all the mass is fission at once. And that's really not the true case, for instance, in an atomic bomb. Okay. So there has to be a certain amount of mass of these fissionable and unstable atoms that come together to form a critical mass. And then once this happens, we don't really need any external source of neutrons. When we achieve this certain critical mass, this reaction can go on spontaneously. All right? Yeah, of course, we need 1 initial neutron from the get-go, not to occur naturally from fission, self-fissioning itself. But we have now a critical mass. So for instance, uranium-235, what do we have over here? 15 kilograms at 33 pounds. All right, this now can progress spontaneously. All right. Okay. So of course, we don't want this rapid release, this rapid chain reaction to go on, except of course in a nuclear bomb. We want this to go in a very controlled, in a very slow fashion when we talk about nuclear power plants. And that's exactly what we have over here. And if you recall now, this is pretty much what we showed in the beginning of chapter 4 when we talked about fossil fuel power plants. It's essentially the same setup, right? The one big difference here is now, instead of burning fossil fuels, instead of burning coal, wood, petroleum, whatever you may have for the fuel source to boil the water, we're now going to use the energy released, the nuclear energy that's being released from these uranium atoms that undergo this fissioning process. So again, this is all pretty much the same. We have the heating reaction over here. We'll talk about this in more detail in just a bit. All right, the fuel rods of uranium are placed inside of the water bath, right? And we heat up the water. This is in a closed loop. This is primary cooling, and the coils, okay, impart its energy, its heat energy, to a secondary system, the secondary coolant, and this is actually the water that's given in blue that's boiled off to form steam. This is under compression. The steam then imparts its energy to mechanical energy if it has work that's being done onto the turbine. The turbines turn a dynamo and a generator, okay, you produce electricity. The steam is then condensed and it forms water to be reheated and form this certain loop. All right? We have a third system over here where we have the cooling. All right? And this is where we have to cool down this steam into condensed water so it can be boiled off again. So it can go a cyclic process. All right? So this facility over here is in a dome structure, as you see in a very familiar picture of nuclear reactors, at least in the United States, that is. Okay, we have the dome structures, even the photo over here. All this system over here, the cooling tower, this is what's in this sort of, odd-looking shape when you see a nuclear power plant on the horizon. And I think there's one, St. John's River in Blackett, in Florida. I drive past it when I say Augustine. All right, you see down the river, you see the cooling towers, you see this coming out of here, this smoke, okay? It's not smoke. That's water vapor, condensed water vapor being produced from the cooling process over here. All right, so no smoke is produced, there is no combustion, it's a fallacy, this is just pure water coming off. Okay? So a little more in depth now about the actual reaction center. What we have now are these fuel pellets of fissionable uranium, okay, uranium-235. Remember we said this is about 4 grams or so, a little smaller than a dime. We have about 200 of these pellets lined up in a fuel rod, okay? And we have very many of these pellets in a fuel rod, and these rods are then arranged in this fuel assembly. And it's this fuel assembly which is placed permanently inside of this primary coolant, this water bath, which is under extreme pressure, 150 times the atmospheric pressure to prevent the water from boiling. Okay? So we all say that water boils at 212 Fahrenheit or 100 degrees centigrade, and that's true at atmospheric pressure. I mean, for those of you that went to Denver, for instance, the water boils at a lower temperature. You put water boils at a lower temperature in Denver, for instance, because there's lower atmospheric pressure. Well, conversely, if you apply more atmospheric pressure, the water boils at a higher temperature. You get more heat being put into that water, for instance. Okay? So this is under very, very high pressure to get that water very, very hot, well above 100 degrees C. Okay? And we have next going in here are control rods. This helps regulate the process which, without these control rods, this fissioning process would go to an uncontrollable extent. So this helps control. All right? Also, we have the primary coolant. Another controlling feature is with a aqueous solution of boric acid. Okay? Boron is a very good neutron absorber. It helps to regulate the amount of fissioning process that goes on. Okay? Another thing over here is that these control rods, I should say, just reminding me right now, is composed of cadmium. Cadmium is also a very good neutron absorber. There are just some elements that have some personalities by their physical makeup, and cadmium is one of them that just likes to absorb neutrons without going under any really catastrophic or uncontrollable fissioning reaction. They don't really fission at all, to a certain extent. Okay? Those are used for the control neutrons. All right, so we got to know this. We got to know the outline of a power plant. All right, for quiz or class. actually it's like important. So, okay, no combustibles, we do have nuclear energy, nuclear fuel that's going on. There's always that certain fear of a nuclear explosion, all right? And this was actually realized in about 1979 when we had the 3 Mile Island accident. Now, coincidentally, all right, 1979, March 16th, there was a movie released, all right, called The China Syndrome, where, you know, it was talking about a potential nuclear meltdown and the catastrophe that would ensue afterwards. The reason why it's called China Syndrome is because when we had a nuclear reactor, okay, that core, well, that could get up to a very, very high temperature, and the fear was that it would get so hot that it would melt all the bedrock, all the concrete that supported it, and melt right through the earth and go to China. Okay, that really doesn't happen, of course, but there was certainly that fear, that uncontrollable heat. Really, how do you stop this process? There really is no way, to any reasonable degree, to stop that process once it goes on uncontrollably. I mean, look at a nuclear bomb, for example. All right. So again, China Syndrome for that reason. And funny as it may seem, that 11 days later, after the premiere of that movie, we had the 3 Mile Island accident. All right. So what happened was 3 Mile Island, okay, outside of Harrisburg, southeast region of Pennsylvania. All right, lost a little bit of coolant. All right, it was a stuck valve, a little bit of human error, and of course there was a partial meltdown. All right, it was able to be sustained and controlled. Unfortunately, though, there was some radioactive gases which were released. And what happened was it really scared the crap out of a lot of people in the country. And again, moratorium was placed on any new production of nuclear facilities. And it's unfortunate, you know, accidents do happen. There really wasn't anything that was going on over here. Nobody got cancer, nobody died from this. But, you know, politics in America are kind of touchy. All right? I mean, I was on a live then, so I would not say, you know, really what was going on at the time. But a lot of people obviously felt fearful enough where the energy is now on the decrease, certainly in our country. You may have heard of Chernobyl. This occurred in 1986. All right, this was, in fact, a full meltdown. This was, in fact, a extremely catastrophic event. All right. What happened was, during a routine safety check, all right, the coolant water was actually halted. So there was no coolant water going in. And in fact, there was a little bit of human error. And again, if you saw 60 Minutes on Sunday, they attributed the Chernobyl accident to sleep deprivation. So what happened is that poor design, human error, okay, a lot of miscommunication, resulted in this meltdown where the reaction occurred uncontrollably. There was no way to really shut it down in a reasonable extent. You have now superheating of the pellets, okay, because they're going to keep on going without any sort of control process. The pellets became so hot it actually melt the rods that were contained, all right, and it melted the graphite or carbon control rods. So we talked about cadmium in U.S. reactors. In Russia, in particular, this plant, they use graphite. When the graphite became so hot, it undergoes this reaction which we just saw in the last lecture. You have hot carbon and hot water in the form of steam, for instance. Well, remember we said before water gas? What happens? You produce hydrogen gas. Remember we saw when we did the sodium demo over here, when hydrogen gas gets hot enough, that's certainly going to combust. And that's exactly what happened here. In Chernobyl, there was no nuclear explosion. There was no ever any way of a nuclear explosion to occur in a nuclear facility. This was indeed a chemical explosion. This was hydrogen gas combusting, like we saw in the balloons, here in class, like we saw in the sodium metals. All right? Unfortunately, though, it blew the crap out of the whole reactor, okay? And an amazing amount of radioactive material was released. Overall, until the reaction, the fire was controlled, which was 10 days later, about 100 times the radioactivity of Hiroshima was released. Really incredible tragedy, right? A lot of people died, as you might expect. All right. So immediately, several workers were killed. 31 firefighters that were helped to control the fire, because there was an actual just combustible fire that was going on, died. About 150,000 residents in the surrounding area, about 40 miles radius, were immediately evacuated. All right. Because without that, they would certainly die, if not in the immediate term, in the short term, with severe radiation. So 150,000, that's about the population of Tallahassee. Just gone. That whole area now around Chernobyl in southeastern Ukraine is just deserted. Right, it's actually at 60 Minutes a few months ago. I really like 60 Minutes. And what we have over here is, after the fire, all right, Soviet Union called in about 200,000 volunteers, all right. Now, you know, this is communist Russia, or communist Soviet Union. When we call volunteers, what they call volunteers, we may have called, you know, slave labor, prison labor, for instance. All right, we can't really prove that, but I really doubt there'll be 200 people running to a burning nuclear reactor. All right, this is pretty much going to be under duress. And what happened was they built this very large sarcophagus. I mean, really, what else can you do? All right, they pumped in a whole bunch of boron because it's a good neutron absorber from the air. All right, with the helicopter, and they just really didn't know what to do with it. What do we do? They just decided to put a whole big shell around it, concrete and steel, massive amounts, and they just contained it. Just let it sit there. They just, you know, sort of walked away. Right? What else can you do? Trash. Okay. Total cleanup cost, including the loss of productivity. We consider all the farmland and value. All right, about $360 billion. That's a conservative estimate. All right. And of course, this may happen in our country, certainly. But let me be perfectly clear here, there is absolutely no chance ever of a nuclear power plant blowing up, okay, as a nuclear bomb. That's just not going to happen. There is not the capability. Why is that? Well, because there are certain safety systems deployed, okay. Certainly in the United States, we have an incredible amount of regulation, all right, the DOE and the Atomic Energy Society that we have, all right. Also, in U.S. power plants, you're going to see this sort of dome structure, which you did not see, for instance, in the Chernobyl facility. This dome structure is where all U.S. reactors are stored. This is a very, very thick steel and concrete wall, up to 4 feet thick. All right, it's actually built to withstand direct impact of a B-1 bomber, I believe. All right. Again, there's no impact or no danger from a nuclear explosion. Why is that? Because we use very, very small amount of visual uranium, all right? Naturally occurring 235 is about 0.7%. We enrich it a little bit. We'll talk about the enrichment process on Friday to about 3.5%. All right? For a nuclear bomb, you need a lot more than that. All right? So no critical mass is ever reached. No explosion will ever occur. That's it. We'll see you again on Friday.